Well, welcome back. And the topic today is to continue our discussion of this Lipkin model. And then we are going to move into the particle-hole formalism, which will simplify things a lot. Now, one of the things I wanted to show you with this Lipkin model, where the first exercises are more about using the quasi-spin operators and the anti-commutation relations, and show that these quasi-spin operators, which we defined, that they obey the same relations which you have for angular momentum. So you have specific commutation rules, and you can also rewrite the Hamiltonian in terms of these quasi-spin operators. And that is going to simplify the calculations of the so-called Hamiltonian matrix. So the next week, when we are going to discuss full configuration interaction theory, then you will find this way of setting up what is called the Hamiltonian matrix for diagonalization as a very efficient way. But let's now go back to one of the exercises with the Lipkin model, which deals with the calculation of the ground state expectation energy. And that's the last exercise this week. And the reason why we are going to go through this in this very, how to say, tedious way is simply because we want to motivate the particle-hole formalism. So let's just use as a header the particle-hole formalism. And this is something which is common in a broad sector of fields in physics: quantum chemistry, condensed matter physics, nuclear physics, etc. So we are going to motivate this now by looking at the Lipkin model. So the example which we are going to take is the Lipkin model with 4 particles with n equal to 4. And we are going to make an ansatz of the ground state. So let's just quickly remind ourselves of how this looks like. So we have a spin quantum number, which we put a label minus, we gave it the value -1. And then we have these 4 slots here, which now indicate different single particle states with quantum number p. And then we would have the same slots up here, but now with a spin equal to +1, but we would have the same quantum numbers, 1, 2, 3, 4. Now we are going to make an ansatz for the ground state, where we now assume that the ground state is given by these 4 lowest lying states being filled. And we are going to rewrite it in terms of the notation we have used before. So this will be an A1 with spin minus. I'm going to just put a minus here. A2 with spin minus, A3 with spin minus, and A4 with spin minus acting on the vacuum state. And this is the value of sigma, which you see here. And we defined the creation operators in terms of AP sigma acting on vacuum. So that creates a state, a particle in a state P sigma. So what we're going to do now simply is to calculate the expectation value of the Hamiltonian. And we defined a single particle operator for the energy, which we call for H0 as usual. And this is given by 1/2 of epsilon. And then we have a sum over P and sigma multiplied with sigma, and AP sigma dagger AP sigma. So let's calculate the expectation value of that quantity. So we are going to use Wick's theorem. And Wick's theorem and this kind of more brute force approach, where all the single particle states are particle states. So we have the vacuum as the reference state. This is still something which is doable. So we are going to have a sum over P and sigma. And then we have sigma and 0. And then we're going to have A4 minus, A3 minus, A2 minus, A1 minus, and then we have AP sigma, and multiplied with A1 minus, and A2 minus, and A3 minus, and A4 minus. So this is a case where all the spins have to be minus, because else we will get zero contribution. So when we perform contractions. So I'm going to simplify the notation now, and I'm going to drop the spin value, because this state which we have chosen has all spins pointing down, or -1. So there's only one spin value. So let's take away the spin degree of freedom and just put that one to -1, because if you now look at the possible contractions which we are going to do, I mean, the sigma values have to be minus. So I'm going to take away the spin degree of freedom, and it means that since we only have one value for the spin, this is minus, so we're going to get 1/2 minus 1/2 times epsilon, and then I have the sum over p, and now things simplify a little bit, because I would have A4, A3, A2, A1, AP dagger, AP, A1 dagger, A2, A3, and A4. Now, if you look at the contractions here, when I contract P with 1, then since P is the same in the creation and annihilation operator for the operator of the energy, for the one-body operator, then clearly this has to be accompanied by that one. That's the only possibility. If I contract AP with A1 dagger, that means that I have delta P1. That means that any of these other contractions here has to be equal to 0. Okay? So that means that in this, yeah. Say it again. You
explained some of the terms are 0.
No, if you now look at the possible contractions you have, if I now lock the contraction P with 1 in this term here, then this has to be contracted with that one. Because if I were now to contract this P with that one, then I have defined that I have a Kronecker delta with P1 equal to 1, then I cannot have P equal to 2 as well, right? So the only possibilities which you have then, when you have chosen this, is now that A2 has to go to A2. No, that's not A2, but that's A3, sorry. And then A3 here has to go to A3, and A4 to A4. Next time, I let this operator act on state 2, and then I get a similar contribution. So what you will get then is just a chain of Kronecker deltas. And these Kronecker deltas, since we have 4 states, we will get 4 Kronecker deltas. So that means that I get 4 contributions, which are just 4 times 1. So this becomes simply equal to -2 times epsilon. That's what I get there. So you see one thing here compared to what we did earlier when we set up the Slater determinant, is that when we did the Slater determinant in configuration space or in first quantization, we started to look at all the possible permutations. Now here, you see immediately from this more compact notation where you're simply looking at the number of particles in a given state, that when you have contracted the operator with one single particle states, there is only one way you can perform the other contractions. So it's a much more, how to say, simple way to see the way you calculate expectation values. So this is a pretty simple answer. So the next thing we can do now is to take a general expression for the two-body operator. Now, in the exercise, we had a very explicit expression for the two-body operator, but let's set it up in a general way. And as I said, we do this now since we want to motivate Wick's theorem and the particle-hole formalism. So what I'm going to do now is to keep this more compact notation with states 1, 2, 3, 4, and I'm going to leave out the spin degrees of freedom. So when I look now at the expectation value of the two-body operator, and now we take a general two-body operator, so we don't specify what kind of operator we have. Now, the state which we assumed we are dealing with is now this ansatz for the ground state, where we simply have put all states in a negative spin value. This is just an ansatz. We have many, many other possibilities. And as we saw yesterday, when we did the combinatorics, we had 70 possibilities for placing 4 particles in these 8 different slots. So the expectation value of HI, so let's just keep this pretty general. That leads us to have to consider the following type of contractions. And now I'm going to use this more shorthand notation where we just list the operators and we look at the contractions. So that means that what we are going to have then, since we have the state 4, and we've taken out the spin degrees of freedom because the spin is the same. So we have an A3, A2, A1, and then we have the operator, which we would label as an A alpha, A beta dagger, and then I have an A delta and an A gamma, and then I have an A1, an A2, an A3, and an A4 dagger. Now, the operator here acts on pairs only, right? So it's only pairs which appear here. So if I now perform this contraction here, this is just one example, and I'm going to call this the 1-2 contribution. And the 1-2 contribution simply now because the operator acts on state, single particle state 1 and 2. Now, this leaves us with just one possibility. And the only possibility which we have is that we link 1 and 2 on the brass side as well. Because if we don't do that, then we would have to do the contraction of a state 3 with a state 2, for instance, which is by definition equal to 0. So that means that in this particular case here, we are now linking A3. So you can call A3 and A4 as bystanding particles. They are not interacting. Now, if you now look at this case here, you remember from yesterday that this gave us 4 possible contributions when we now look at the possible contractions. And these 4 possible contributions, they gave us 1-2 of V, 1-2 anti-symmetrized, and then we have a delta 3-3 and a delta 4-4. And now you see that what we can keep on doing now is to think of letting the operator act on state 1 and state 3. So the next case is simply to take 1 and 3. So when I write it like this, it means that it is the operator which acts on these 2 states to the right here. So when you look at this specific notation here, 1-2, it means that I'm taking these 2 operators and I'm letting them act on 1 and 2 here. And when you've chosen 1 and 2 here, due to the fact that you have this specific number of creation and annihilation operators, you have to be a little bit careful with the quantum numbers here, which means that when 1 and 2 have been locked here, if I try to let alpha and beta here act on 3 and 4, then I would have 2 and 1 here, which would have to be contracted with 3 and 4. And that would give me 0, because 2 is not equal to 3, and so on. So one way to look at this specific term 1, 2 is now that you have the states 1 and 2. So this would be the diagrammatic way. You have the operator with your alpha, betas, and gammas and deltas. Gamma, delta. And you have 1, 2 coming in. So this is the initial state. And then you have 3 and 4. And 3 and 4 are then to be considered as bystanding states. So they're not interacting with each other or interacting at all. So this is the kind of way you can draw this pictorially. And what is pretty common in these cases, when you draw this type of diagrams, is that you omit those particle states which are linked with a Kronecker delta. So it's pretty common when you draw this contribution simply to leave this out, because these are just given by Kronecker deltas. Now, if I do the same with 1, 3, it shouldn't come as a surprise that we are getting 1, 3, the anti-symmetrized. And then we have a Kronecker delta, delta 2, multiplied with a Kronecker delta 4, 4. And then we can take the next one, 1, 4. And that is going, surprise, surprise, it's going to give us this term, anti-symmetrized, multiply with the Kronecker deltas of delta 2, 2 and delta 3, 3. And then we can look at the next pair, which would be 2, 3, 2, 4. And finally, we will have 3, 4. So if we now go back to the next term, 2, 3, that is simply going to give us, when we perform the contractions, 2, 3, V of 2, 3, anti-symmetrized of delta 1, 1 and delta 4, 4. So let me just rewrite that one so you can see that more clearly. It's delta gamma A1 dagger, A2 dagger, A3, and A4. So this particular case means now that I'm interchanging the operators A2 and A3 with A1. So I'm performing this contraction and that contraction. Now, if I'm going to contract the two creation operators in the operator with another state than 2 and 3, then I would just get 0 again. So that means that the only possible contraction here, which is non-zero, is this one plus 3 other ones. And the bystanding lines are now going to be 1 to 1 and obviously 4 to 4. So this would be the bystanding lines. And then I can do the same thing with 2 and 4. And that is just going to give me 2 and 4, V, 2, 4, anti-symmetrized. And then I have the Kronecker delta 1, 1 and delta 3, 3. And the final one has simply to be 3 and 4. So that's the final term. And that is given by 3, 4, V, 3, 4, anti-symmetrized, delta 1, 1, delta 2, 2. So that means that the energy is going to look like as follows. So we will have a total expectation value for the Hamiltonian, which is given by the one-body term, minus 2 epsilon. And then I can rewrite the next term as a sum over 1/2. I'm double counting, but then I have this factor of 1/2. And these numbers go from 1 up to 4. And then I have the matrix elements Ij, V, Ij, anti-symmetrized. Now, if we now look at the specific Hamiltonian we have, if we go back to this Lipkin model, now the Lipkin model had a two-body interaction which linked states with different spins. Now, in our case, we don't have states with different spins. So it means that the state I and j here, they have to have the same spins. So if we just remind ourselves shortly about that Hamiltonian, what we looked at yesterday was a Hamiltonian which had two terms. So one term which we call for an H1, that was a term which allowed us to actually promote two particles to the state with the opposite spin. So that means that what we had then, in our case, so we could have these two states here, which stay in 1 and 2. And then they could promote it, and this has a sigma equal to -1. And then we have, so these two states are occupied. And then it gave us non-zero matrix elements only if we had a case where we had two particles with different spins. So when you're going to plug in the expectation value of the Hamiltonian, and you're going to plug in that specific one, which you have for the Lipkin model, then you see that in the specific case which we have here, these i's and j's, they have the same spins. So that means that I'm not going to have any contribution from H1. And if I go back to this H2, which we had, that was a Hamiltonian, which then took into account the interactions. So we could think of 1, 2, and 3 being occupied. And then we could have one of the particles being in this spin +1 state. So the Hamiltonian then actually requires that you have one of the states being in another spin state. But since we have defined now the ground state, or the ansatz for the ground state, we have simply decided that this state has states with the same spins. And since we calculate an expectation value, there is no way that this two-body Hamiltonian, which we have here, this one, will give a contribution different from 0. So for the ground state to ground state expectation value, or the ansatz for the ground state, this is exactly equal to 0, the interaction term. So the only piece which we are left with then is actually this piece. So for this specific case, what we have is phi 0 of h of phi 0 with that specific choice of interaction piece is simply -2 epsilon. Now we can now complicate life if we want to, and we can look at other states. So you could now think of defining a state phi 1 like that. So for this phi 1, where we differ by one single particle state, so this could be given by 1 in a spin minus, an A2 in a spin minus, an A3 in a spin minus, but then I could have an A1 in a spin plus, acting on the vacuum state. This is not what the exercise is asking for, but in that specific case, then this operator H2 would actually give you a contribution. So these are things which we need to discuss when we move on to states beyond this ansatz for the ground state. Now, one of the main reasons why I picked up this term was simply, or this calculation here, is simply because when you now look at the case with 4 particles and a 2-body operator, this is something which is still doable. But if you have 100 particles, it's not fun anymore. So if you go to more than, let's say, some few particles, these type of equations become very unwieldy. And then we need a more compact way of rephrasing the equations. And this is where the particle-Hall formalism comes in, and that implies the redefinition of the vacuum state to a general reference state, which then can be motivated by the physics which you have at hand. So like in the case which you see here now, if you look at this specific state, you could now think of this as a new reference state, a new vacuum state. So instead of dealing with a plain emptiness, you could now think of defining your reference state or the new vacuum state as 4 particles, which form then an ansatz for the ground state. Then what we are going to do is actually to say that a state like this phi1, which we introduced here, which looks like this, for instance, actually it would be a particle in here, in 1. We can think of this as an excitation of the ground state in terms of us having promoted a particle which was here to actually a state which is here. And we will call this a 1 particle, 1 hole excitation. So that's a specific way of just labeling these states here. So let's bring in this new definition of the vacuum state, because this leads also to a rewrite of the Hamiltonians. So we are then going to rewrite the Hamiltonians here in a different normal ordered form. So remember now that the Hamiltonian is always normal ordered, as we can see here, which means that the creation operators are always placed to the left. No, yeah, to the left, yeah, right, left. So, and then being placed to the left is what we normally call for normal ordering of the operators. Now we are going to rewrite them in terms of the new vacuum, but that is going to add a constant term. And that constant term is going to be given by this quantity here, which we will call the reference energy. So that's going to be the difference from what we have been doing till now. So let's, after these words, let's now just look at the particle hole formalism. So when we have been looking at a specific state, and often we start with the ansatz for the ground state, we can think of filling in all single particle states up to a given level. In particular, if you're dealing with fermions. So what we have is a set of single particle states which are being filled up to the Fermi level. So F, and if we have n particles, the last state here, something which we could label as n, this would be n minus 1, 1, 2, 3, etc. And then obviously, in many, many cases, this single particle basis is given by an infinite orthogonal basis, which means that in principle, this sum goes to infinity, but we would always truncate it at some level. And this truncation is something which we often refer to a little d, or dimension, or as we have been using till recently, just a little n. So the little n is normally referring to the single particle states. So in this kind of labeling, then this will be state n plus 1, n plus 2, etc. till the final little n state. So then we would have an ansatz for the ground state, which is typically given by A1, A2 dagger, up to AN, acting on the vacuum, the reference vacuum. And we know that when we act with an creation operator on these states, which are not, so in this state, n plus 1 is not included. So when I do that on phi 0, this is the same as we have to interchange it, so we get it in the right order of A1, A2 dagger, all the way up to AN dagger, AN plus 1, acting on a true vacuum state. So this becomes an n plus 1 particle state. Whereas the previous one is an n particle state, okay? And this kind of nomenclature means often that when we now look at this type of system, what we would have, if we now act on this with an annihilation operator, just to quickly remind you of the kind of notations we had, if we act with this one on this state 1, 2, 3, up to n, which is the same as A alpha, and then I have an A1, A2, and then if alpha is included, there is an alpha minus 1, an A alpha plus 1, and all the way up to A of n dagger. Then we know that we have to perform a series of permutations using the anti-commutation rules. So here we are assuming that alpha is included in this set 1, 2, 3, etc. up to n. If it's not included, then we know that this is exactly 0. So this is the only case which gives us a non-zero result. And this action here, when we now order it properly, is going to be given by minus 1 to the power of alpha minus 1. And then I would have an A1, A2, up to an A alpha minus 1. And then I have an A alpha plus 1, all the way up to A of n. And this state which we have here now is an n minus 1 state. Okay, so these are just a reminder of definitions which we've been working with earlier. It's pretty common to write this state now as a product of all these operators, I equal 1 up to n of A of I dagger acting on 0. And often we use a notation with I less than F. So F now indicates the Fermi level. So we are filling all the states up to the Fermi level, and we are assuming that these are filled by n particles. So this is another type of notation which you will encounter. So I hope it's not too confusing here. Now, if we now also go back a little bit to what we did in the beginning, we assume now that this basis which we are making, this orthogonal basis of Slater determinants, is an eigenbasis of H0. This is a pretty common ansatz, and we will use this ansatz throughout the course, except when we look at mean field methods, because then H0 is no longer an operator which has this set of Slater determinants as eigenbasis. So this is an uppercase letter, epsilon 0, and that is the sum of all the states up to the Fermi level of these epsilon i's. And where the epsilon i's are just the eigenstates of the single particle operator, or the eigenvalues. Now, what we are going to do now is to make an intermediate step. And then after the intermediate step, where we're going to visualize and try to explain how we can rewrite the Hamiltonian, we are going at the end to revert back to the old operators, but with a redefinition of the contractions. So we are now going to do an intermediate step, which in a way in the literature has been abandoned, but sometimes it can be useful when we want to look at the way we are going to rewrite a given Hamiltonian in a particle-Hall formalism, and why we get the expressions which we get. So this intermediate step is more, you will actually find this in many textbooks, but people tend to revert back to the original operators. So we are going to define a new set of operators where we have an operator B of alpha, a given state alpha, which is defined as follows. In terms of the old operators, it's an A alpha if alpha is larger than the Fermi level, and it's an annihilation operator if alpha is smaller or equal to the Fermi level. So you can always perform a transformation where you redefine new operators in terms of previous. So this would just be a linear combination of the two. And then you will have a beta B of alpha, which is going to be equal an annihilation operator if alpha is larger than 0, the Fermi level. And then it's going to be an annihilation of a creation operator if alpha is smaller or equal to F. So what we are saying is that we are going to create a state in in case alpha is less than F, which we are going to call for a whole state. So this, in a way, creates a so-called whole state below the Fermi level. So B alpha, that creates this operator which you have here, B alpha dagger, that creates a vacancy if alpha is below F. So that means it takes away a particle. And we say then it creates a hole. On the other hand, B alpha here, that destroys a particle in a state if alpha is larger than F, and then it creates a particle in case alpha is less than F. Okay, so one B alpha dagger creates a vacancy, a so-called whole state, if alpha is less than F. Now, you can easily see now that the standard anti-commutation rules apply here as well. So for this type of operators, you're going to have the standard anti-commutators, which we had before. Equal to 0. If I take these operators and perform the contraction, this is going to be delta alpha beta. And then it's also easy to see that B of alpha, B of beta has to be equal to 0. So when I act with this B alpha dagger on a state phi 0, then I have to be careful a little bit, because this is equal to A alpha dagger on phi 0 if alpha, sorry, not that one, if alpha is not contained in phi 0, because if it is contained, it is equal to 0. So this adds a particle on top of your state. And that means that you have, instead of have a state with n particles, you end up with a state with n plus 1 particles. And then you see also that the action of this operator here, this is equal to A alpha of phi 0 if alpha is included in phi 0. And we can do the same exercise with the other operator. So let's now look at what happens if we rewrite the number operator in terms of these new creation and annihilation operators. So what we're going to do now is to look at the number operator, which we previously wrote as a sum over alpha. This sum runs over all possible single particle states. So just remember now that you have an infinite basis of single particle states. And in principle, this runs over all the single particle states which you have available. Now, what I can do now is just to split this sum into two sums. So I would have one sum where alpha is including the states up to the Fermi level, plus one where I simply have alpha larger than the Fermi level. There's nobody which hinders me doing that, right? Now, I can then rewrite this in terms of these new operators. So if I now introduce the new operators, what I get is a sum over alpha larger than F, where I can simply rewrite this as a B alpha dagger times a B alpha, if I use these definitions. And then I have a new sum, and where I now have to be a little bit careful, because now I have a B alpha or B alpha dagger. So I'm just specifying that these are states below the Fermi level. Now, if you now look at what I've done here, this second term is no longer normal ordered. And that makes it more tricky to use with Wick's theorem. But what I could do since I have these nice anti-commutation rules, is I could simply use them, and then I know that B alpha dagger plus B alpha of B alpha is equal to delta alpha alpha. Not very exciting. So that means that I can rewrite this now in terms of a sum over alpha larger than the Fermi level of B alpha dagger B alpha, and this is normal ordered, minus one term which is also normal ordered, because when I'm acting on a state, I want to keep everything being normal ordered. But then I have now a Kronecker delta, which means that since I have a Kronecker delta here, this Kronecker delta is now something which applies to the states below the Fermi level. So if you go back here, we have a sum over the Fermi level, and now I have a Kronecker delta. So this sum is limited to up to the number of particles. So what this does is that it simply gives us the number of particles, because we are summing now up to the Fermi level. And we are thinking now of having all the states occupied by n particles. This quantity which you see here is normally called a reference value. So this is a reference value. If we now think back to the calculation we did last week with the number operator, and we took the ansatz. So what is this reference value here? So last week, we calculated the expectation value of an ansatz for the ground state. And this guy here is now given by this alpha less than f of A alpha dagger acting on 0 of the number operator of phi 0. And one of the things we found then is that this expectation value is simply equal to the number of particles. So this number operator simply counts the number of particles you have. So the reference value here is the number of particles. Now, the thing which is nice is that if we go back to the form which we have here, then this is just the operator in a normal ordered form. And this is the form we want to use when we are calculating expectation values. So let's take a look at some further examples here. So we have also, by the way, there's one thing which I forgot to say, is obviously that phi 0, the norm of that one, has been put to 1. So this is just a piece of information which I forgot to tell you. So when I am now calculating the vacuum to vacuum expectation value of this normal ordered operator, what happens then is that when I take phi 0 and I have a normal ordered operator of this chain of operators xy of phi 0, then if we follow Wick's theorem, this is exactly equal to 0. So normal ordering the chain of operators means that we can use Wick's theorem as before. The only difference now is that we have this reference value which comes in addition. But when we now take this expectation value of the ground state to the ground state, for instance, then we're actually going to get an expectation, with normal ordered operators. This is actually going to give us 0. And you can see that if you plug in these operators. Now, what we can do now is to define new states. So let's look at some examples. Yeah, we should do that actually. Yeah, we start a little bit later, so we should take a small break here. That's a good point. So let me just pause the recording here. Before the break, we went through the introduction of new operators. And we are going to use these to now motivate a little bit more the way we rewrite a operator in second quantization in a new, with a new set of operators, which are then defined for a new reference state. And sometimes we just loosely call this just a new vacuum state. But I will try to use a reference state, which I think is a better naming. So we can define, with these operators, we can define new states. So we have an creation operator, beta alpha, and beta, no, B beta, which acts on this reference vacuum state. And now we could assume, we can make an assumption here, if we want to make the comparison. So we are creating two new states. What are these states? We can now make an example where we let alpha be larger than F, and we have beta less than F here. So what that means is that if we go back to the original operators, we have a creation operator, and we have an annihilation operator. So we're actually removing a particle from a state beta below the Fermi level, and then we are creating a new particle in a state alpha above the Fermi level. So this would just be an example of a new state which we can create with this set of operators. So what does it mean pictorially? So a picture which we can make of this new state using the definition of all the single particle states up to the Fermi level. So we have filled in 1, 2, up to n minus 1 and n. So suppose we have the state beta here. So this particle here is now taken away from that slot. So we create an n minus 1 state, but then we act with the creation operator. So we have a state n plus 1 and n plus 2, and up here there is a state alpha. And now we promote this particle, which was in the state beta, to a state above the Fermi level. So what we call this for is a one particle, one hole excitation of the reference state. This is just a way, just keep this in mind, this is a bookkeeping for how we can rewrite or redefine all the determinants which we can make when we have a given single particle basis which ends up here in n. So these continue up to little n. So the total number of configurations which we can make, as we said yesterday and also in the beginning of the semester, is given by the n slots we can place the particles in, and then we have n particles. So this is the combinatorics we have with fermions. When we are filled, we have the possibility of having either 1 or 0 particles in a given single particle state. So this is a state which we will call a one particle, one hole state. This is an L, one particle, one hole state. Or, as we are going to use as a shorthand, 1p, 1h. And the kind of notation which I will use then is a phi. And now I have a whole state as a subscript. And I have a particle state alpha as a superscript here. So this is my one particle, one whole state, which is the same as a, so these are just notations which I'm introducing now in order to simplify my nomenclature. Okay? And the way you can think of this is just as you redefining one of the possible ways of distributing these particles in little n slots. And then there's nothing which now hinders you of taking a B alpha, B beta, and then a B delta. So this is an anti-symmetrized operator, and then it acts on phi 0. And now you can define alpha and beta to be larger than F. And then we can have delta and gamma, because if these are states above the Fermi level, all of them, that means that we would create an n+4 particle state. But now we could assume that these states here are all, this gamma and delta are below the Fermi level. So if I now bring back the old operators, this is the same as A alpha, A beta, sorry, this is a beta, and then I have an A delta and an A gamma acting on phi 0. And this generates, it takes away two states below the Fermi level, and then it creates then an intermediate n-1 Slater determinant, and then I add two particles, and then I'm back to n particle state. But this would now be a two particle, two hole state. And you can see that if you visualize it. So you can think of 1, 2 here, and then you have your delta, and then you have your gamma here. So these are occupied, and then you have the final one, n up here, and then you go above the Fermi level, and then you have some state up here, some beta, and then another state alpha up here, and so on. So you produce a vacancy here, and then you have two particles now placed in that state. So that's called a two particle, two hole state. And then you can continue like this. So this is just, again, a way of reordering the list of possible configurations. Now, if this little n, which we had up here, goes to infinity, you have an infinity of two particle, two hole states. And you have an infinity of one particle, one hole states, etc., etc. But since we will always truncate the infinite basis to a given number, little n, that means that we would have a finite number of one particle, one hole states, a finite number of two particle, two hole states, etc., etc. Now, there are some useful things now, which are worth taking a closer look at. And we are now going to look at the number operator again. Now, not the number operator, but the Hamiltonian of the system. And we are going, because before the break, we rewrote the number operator, which we have here, in terms of the new operators. Now we're going to do the same exercise with the Hamiltonian. So let's take a look at the rewriting of the Hamiltonian. So we have H0, which is given by a sum alpha beta, and we have this matrix element alpha H0 of beta of A alpha dagger A beta. This is the operator in its most general form. Now, what we're going to do now is to simply introduce the new operators. So we're going to rewrite it in terms of sums of for states below and above the Fermi level. So we can rewrite this one with alpha beta larger than F. So this is alpha H0 of beta. And then we introduce the new operators. So these have simply to be equal to these terms here. So I'm just introducing the new operators. And then I will have a new sum where I have alpha larger than F, and then I have beta less than little f. So that's one possible contribution. And then I have alpha H0 of beta, and then I get beta alpha. But since beta is larger, now less than f, less or equal, then this becomes a creation operator. Then I have plus, and then I have alpha less than f, and beta larger than f. And this is something which becomes equal to alpha H0 of beta, and then I have B alpha, and then I have B beta dagger. This is not normal order. So we are going to try to normal order that one. No, sorry, that was not that. the one I was going to write. This was actually the next line in my notes. So this is given by B beta. And then I have a final term, which has alpha and beta less than the Fermi level. And I have alpha H0 of beta. And then I have a B alpha dagger, B beta, nope, not a dagger, like that. Now, the last one is not normal ordered. So we want that one to be normal ordered. And we are going to use the same trick which we had previously. So if you think of this term B alpha, B beta, we are going to rewrite this one as a delta alpha beta minus B beta dagger or B alpha. So that's for the last term. Now, the two intermediate terms are two terms which we can manipulate by simply interchanging beta and alpha. So let's try to do that. So we can rewrite this term here in a simpler way by interchanging the variables alpha and beta, because these are just dummy variables. So when I collect everything here, I can actually rewrite using this expression here. I get now the following expression. So I'm going to have a sum over alpha beta larger than F, where I have my alpha H0 of beta, and then B alpha, B beta, like that. And then by simply interchanging the two indices, I'm going to rewrite them in terms of just one sum, but that will contain two terms. So there's going to be a term alpha of H0 of beta, and then I have a B alpha, B beta dagger, plus a term beta of H0 alpha, and then I have a B beta, B alpha. So that's the second term, which I've rewritten. I did the second and the third term, which I've rewritten just in a more compact way. And then I'm going to have a Kronecker delta, which now has a sum only over alpha. And then I have my alpha of H0 of alpha minus a sum over alpha beta less than or equal than the Fermi level of alpha of H0 of beta. And then I have a B beta, sorry, dagger of B alpha. So everything is now written in terms of a normal order form. Now, one thing which we have often assumed in this course, and this is pretty common, is that the basis which we choose as a computational basis is an eigenbasis of H0, which means that we would typically replace this one with an epsilon alpha. And if we then go back to this definition of the reference energy from H0, so we remember now that this phi 0, this is the vacuum state we have now redefined to be, or just a reference state. If we take that one, we know that this one is equal to simply the sum over all the states up to the Fermi level. So this is normally called the reference energy, because we are calculating that with respect to the reference state or the new vacuum state, reference energy for H0. And this is a quantity which we called for an uppercase letter epsilon 0 here. Okay, so you see now that we have a expression for the operator which now contains a constant, but everything else is normal ordered. So if we go back, we see now that this term is normal ordered. This is obviously normal ordered. Same with that one. And then we have the same for that specific term. And we have an additional constant, which is similar to what we had for the number operator before the break, because in the number operator, we just had the expectation value, the vacuum-to-vacuum expectation of the number operator, which is a number of particles. So every such operator with respect to the new reference state are going to be rewritten in terms of a chain of normal ordered operators plus some constant, which we call for the reference value. Now, if we now look at the expectation values here, if we go back to the expression which we had, so this specific expression here, and we're now going to calculate an expectation value. If you now take the expectation value of the ground state, so if we take this specific expression which we have in the new form, and we calculate this explicit expression, this explicit contribution here, what we would have then is a chain of operators where we would need to calculate the expectation value here of phi 0 with phi 0 here. Now, this is normal ordered. So these are states above and below the Fermi level, which means that since this is normal ordered, when we calculate the expectation value, this is going to give us 0. This is just like as we had before, because this state beta is not included in the vacuum state. So what I end up doing then is to act on the vacuum state, the new vacuum state, with an operator which now simply says that I'm going to create a particle, a destroy one, which doesn't exist in the vacuum state. And that gives us 0. Here, on the other hand, we are trying to create a state. So we would be creating a state in quantum numbers alpha, but then when we calculate the expectation value with a vacuum state, here we will have destroyed a state below the Fermi level, but then we create one with alpha here above the Fermi level. So that means that we are going to get another contribution, which is going to be 0. The same with this contribution, and the same with this contribution here, because that's also normal order. Because this translates into a creation operator for holes. And we are trying to create a state below the Fermi level here, which is already occupied. So that means that for the ground state, if I now take the expectation value of this quantity here with a new operator, I'm simply going to get this term back again, which we should get. So the thing becomes more interesting now when we are looking at the expectation value between excited states like one particle, one hole states, and one particle, one hole states, or the ground state and a one particle, one hole state. So let's take a closer look at that. But what we will be doing now is to change the definition which we have and go back to let's take first an example where we use this definition of the operators. So let's look at a state which we call for phi. So this is a one particle, one hole state of phi of gamma of delta. And now I want to calculate the expectation value where I go from that state back to the same state of H0. Now, this specific state is now given by a B, these new operators of a delta, dagger. So I'm creating a particle state. And now if you go back to the definitions which we had, since this gamma is an explicit whole state, or state below the Fermi level, that means if we go back to the definitions which we brought in before the break of these new operators, so let's just bring it back, then I know that if I have a state below the Fermi level, I'm just destroying a state below the Fermi level, then I need this term here, which I then would rewrite in terms of that operator. So let's go back to where we were. So this specific state which we're having is going to be given by a B gamma dagger acting on the vacuum state, the new vacuum state, with those operators. So what we will end up with then is a set of operations where we have phi 0, and then I'm going to have a B gamma, a B delta, and I have now the operator, which I just write as an H0. And this contains now B delta or B gamma dagger of phi 0. And what we can do now is to look at the different terms which we have for these operators. So we have the terms which are defined explicitly for states above the Fermi level, and states above and below the Fermi level, and just below the Fermi level. So let's take a closer look at what we get here. Now, one thing which is pretty obvious is the term which gives us the reference energy, which is the term which we defined here, this one. That is just a constant for the operator. So if we have a constant in this expression here, then that is something which we just can pull out. And then clearly the only contractions which are possible are this guy with that guy, and this one with itself. So these would be the only possibilities which we have for the constant term. And that gives us then obviously the constant term, right? So the constant term will appear again. And it's pretty common when you're looking at the problem to scale away the constant term. Okay, so when you then do the contractions, we will need terms of the following type. So we will have a B beta, B gamma, B delta, and then I have a B alpha dagger of B beta, and then I will have a B delta of B gamma, like this, no, like this. Now, we would have a term where alpha and beta are larger than the Fermi level. Now, delta is larger than the Fermi level, and gamma is below, because we have defined them to be particle Hall states, right? So for that specific case, the only possibility which is non-zero is this one, because delta is above, by definition, above the Fermi level, the way we define that state, as you can see here. So we have now defined this as a particle state and this as a Hall state. So that means that the only contraction which is possible is this one, for that part of the operator. Then we have the case where one of these alpha can be larger and beta can be smaller than F. So in that specific case, we had B gamma, B delta, and then we had a B alpha dagger, and then we had a term like this one, B beta dagger, and then I had a B delta dagger or B gamma, like that. Now, in that particular case, we're actually going to get a contribution which is going to vanish, and you will see that. So you can also have the case where you have beta, if you have beta larger than F and alpha less than F, this term here would then be replaced by this B beta or B alpha or B delta or B gamma. And you see that in that specific case here, and as we discussed in connection with Wick's theorem, you have now 4 creation operators and 2 annihilation operators. And in this other case, we have 2 annihilation operators here. There are 2 more here. And that means that we are actually, in this particular case, we are going to have 5 annihilation operators and 1 creation operator. So this is also automatically going to be 0. So the term, in addition to the constant which we had, which is going to give us something which is non-zero, is actually this term which comes with a minus, and where we had a sum of alpha beta less than the Fermi level, and then we have this phi 0, and then I have a B gamma, a B delta, and then I have a B beta plus, a beta alpha. So beta and alpha are both below the Fermi level. And I have a B delta times a B gamma dagger. Actually, this should be like that. In that specific case, what we are going to have now are contractions like this and contractions like that. And then delta goes to delta. This is the only possibility because we have defined gamma to be below the Fermi level. So gamma is below the Fermi level and alpha, delta is above the Fermi level. So if we look at these contractions, which we have here, this will give us a, put a line in addition to that one. This term here gives us delta gamma gamma. And then I have a delta alpha delta, a delta beta delta. And that is going to give us a specific contribution here, where we will have a term which was alpha H0 of beta, which is simply a state with the energy above the Fermi level. So this is going to be equal to an epsilon alpha here, or actually an epsilon delta. So that's a state above the Fermi level. This comes as a state below the Fermi level. So this is going to give us a delta gamma beta, a delta delta delta, and a delta of alpha of gamma. And the alpha and betas and gammas are less than the Fermi level, below the Fermi level, which means that this is going to come with an energy minus epsilon of alpha, which is where alpha is now a state below the Fermi level. So when I collect everything, what we will get is the following. So I have an epsilon delta, just that one, where delta is larger than the Fermi level, minus an epsilon gamma, where gamma is less than or equal to the Fermi level, plus a sum over alpha less than or equal to the Fermi level of epsilon alpha. So I have the difference between the particle energy and the whole energy. And this is often very, very useful because in some cases, like in nuclear physics or in atomic physics, when you're looking at what is normally called magic numbers, you can look at experimental energies for kicking out one neutron and keeping one neutron, or what's normally called the neutron separation energies and the proton separation energies. And they can be used to define a so-called gap around the Fermi level for nuclei like oxygen-16, calcium-40. And what you would see often then is that this gap is large when you have so-called shell closures or magic numbers, which one sees in nuclear physics and also in atomic physics. The periodic table has so-called magic numbers. And this quantity, which we see here, is something you can relate to experiment in terms of if you're doing nuclear physics, like some of you are doing, in terms of neutron and proton separation energies. And then you can plot these by looking at the binding energies of one nucleus and another one. And then you can extract these quantities and try to relate them to your favorite theory. But these are numbers which are used as an indication. So if you have a large gap, this often means that you require more energy to excite particles from below the Fermi level to above the Fermi level. And a typical case with a large gap is often related to you breaking these kind of magic numbers. If you're interested in discussing this, I can come back to it. This is a kind of more, how to say, it's an application of this theory to experimental data, and where you try to interpret the experimental data in terms of such differences. So remember now, single particle states, they don't exist experimentally. This is a theoretical construction. What you're dealing with experimentally is always a many particle system. So when you extract an information like this one, you're making an interpretation. So how viable that is depends on the system you have and also your theoretical approaches. Okay. So this is what we would get if we do that, and we can rewrite this in a more compact form. So we have this epsilon delta minus a sum over alpha, and where alpha is different from this state gamma. So before we move on now, I'm actually going to introduce a new notation. And we will use that notation for the rest of the semester. So this is going to be a much more compact notation. And it's a notation which is borrowed from quantum chemistry. And if you go into that textbook, which we have online on the website, on the GitHub address by Hjorth and Bartlett, this is a notation which has been used in fields like condensed matter physics, quantum chemistry, but also nuclear physics. So let's introduce this new notation before we move on. So I'm going to have new labels. And from these labels, we will be able to say whether we are above or below the Fermi level. So the states which we have been filling in, these so-called single particle states below the Fermi level, or as they often are called in a very sloppy way, as whole states. So when I say a whole state now, I may not necessarily mean that I've kicked out a particle from that one, but it's pretty common to refer to these states below the Fermi level as whole states. So we are going to think of this being filled, and then we are going to use labels like I, J, K, L, etc. So this is 1, 2, 3, up to N. And these are normally called whole states. This is just a little bit sloppy language because one should say states below the Fermi level, single particle states below the Fermi level. But then it's easier to say whole state.
It's not whole.
Yeah, exactly. So, and here we have states above the Fermi level, and these are normally called particle states. And I'm going to use indices or subscripts A, B, C, D, etc. And these are normally called particle states. And then we are going to use a kind of general labeling for all states, P, Q, R, S, etc. So these are just all states, all single particle states. And I'm going to put an SP here to indicate that this stands for single particle states. So these are all the single particle states up to N, which defines our effective Hilbert space. So this is just a kind of labeling which you will encounter like in a textbook by Hjorth and Bartlett and many, many other textbooks. So other textbooks may actually label this as a hole 1, hole 2. That's another labeling you may encounter. This could be P1, P2, etc. So these are not real particle states or whole states, but it's just a kind of naming which we use. And these kind of excitations which you look at, like a one particle, one hole excitations, these are normally called quasi-particle states in the literature. Okay, so these are just names you will encounter. And this means that that state which we had, where we put the subscript, indicated a whole state, this is now going to be given in terms of this notation, where we have a whole state, explicit whole state, and then we have a particle state here. And this is the same as BA dagger, BI dagger, acting on the new reference state, which, rewritten in terms of the original operators, is now given in terms of this form here. So I can then define a so this is what we call the one particle, one hole state, 1p, 1h. I can define a new state, which is now given by ij, a of b, and that will be a, ab, aj, ai, acting on the vacuum state. And this is a two-particle, two-hole state. And then there's nothing which hinders me to do a three-particle, three-hole state. A, B, C. And we would simply call this a three-particle, three-hole state. And since I have n particles, I can produce at most n particle, n hole states. So if we go back to this example of the Lipkin model, which we had previously, so if we go look back at that one as an example of excitations or states which we can produce, if you look at the Lipkin model, if we now assume that this defines the ground state with all particles in here, then you see that you can promote all the four particles up here, and that will be a four-particle, four-hole excitation. So that means that this list gets exhausted. Unfortunately, we have an infinite number of single particle states unless we truncate. So it means that in this can just continue up to n particle, n hole excitations. Yeah.
So the two particles that they're
yeah.
Swap the
Yeah, because I want to have the anti-symmetry. But then you have to swap again here. So you would have AJ, AK, no, AK, AJ, and AI. Yeah. So the thing which we are going to do now is also to skip these operators B, because sometimes it's confusing because you need to keep track all the time. And with this kind of nomenclature, it's actually much easier. So we actually go back to the operators A, dagger, and A, which we introduced in the beginning. But now we need to be a little bit more careful with the way we define the contractions. So this is equal to delta PQ if P and Q are larger or above the Fermi level. So this is what we had before. Then I'm going to introduce a contraction which previously, with respect to the true vacuum, was 0. But now, with respect to the new vacuum, this is possible if P and Q, both of them, are less than or lower than the Fermi level. And you can see that now, because if I take the expectation value of this quantity here on the vacuum state, that expectation value, if Q is included in phi 0, then we remove a particle in the state Q. Now then, if P is included, or is a state below the Fermi level, and if it's equal to Q, then I recreate phi 0, and this would be nothing but phi 0, which we have defined to be equal to 1. If it's above the Fermi level, then it's definitely equal to 0. Okay? And we are also going to rewrite these operators which we had in a form where we now have these operators, the old operator. So what we did before the break was to rewrite this one in terms of a sum over alpha above the Fermi level. And we had a B alpha and a B alpha here, minus is alpha less than F, and then we have a B alpha. So this is a normal ordered operator plus N. And we are going to rewrite that one in with a generic sum P here, where we say, or we enforce a normal ordering. So this means that we have a normal ordered with respect to the new vacuum. And later we are going to skip this normal ordering with respect to the new vacuum and just write it as before. But now the subscripts will tell us whether we are above or below the Fermi level. So this is normal ordering with respect to new reference state. And this has plus the number of particles, which is the reference value. We can do the same thing now with the Hamiltonian. So let's just take the one body operator. So we are going to rewrite that one, H0, as a sum over P and Q. It's going to be an integral. And where I have this normal order product of AP dagger AQ plus this reference energy, epsilon 0. So that is a reference energy, which is the energy calculated. Just to remind you, this is going to be phi 0 of H0 of phi 0.
Because it's not a vacuum state.
Say that again?
Because it's not a vacuum state.
Exactly, because it's not a vacuum state anymore. So this is normal ordered with respect to a new vacuum. So one thing which we will start with next week is to calculate, for instance, this expectation value here. So this is the last thing I will set up now. And one reason for why this is convenient compared to what we had previously is that these operators are now normal ordered with respect to a new reference state. So when I look at a one particle, one hole excitation, what I'm going to need to calculate is just phi 0. And then I have the sum over P and Q. And I'm going to have this state AI, dagger, AA, and I have the operator. And then I have my ket state multiplied with a matrix element, P or integral with P and Q. Now the thing now, instead of if now phi 0 has 100 particles, we would have had to look at the contractions with the true vacuum state between that operator and 100 creation and annihilation operators. Now, on the other hand, in this kind of quasi-particle picture, we are simply just looking at the contractions between two operators here, the operator here, and the operator here. And you can see now that when you calculate this quantity, what you would get is something like this. This is a possible contraction, and that one. If P and Q are particle states, then I has to go to I. And then the other possibility is clearly the case where P and Q become whole states. That is going, so when I do this one, when I do this contraction, or all of them, I'm going to get epsilon A minus epsilon I plus this reference energy. So introducing this new vacuum with a normal ordering with respect to the vacuum introduces a term which is just the expectation value of the vacuum, the new vacuum to the new vacuum state of the energy operator. But then we get additional terms. You would have gotten exactly the same expression if you had written this out in the standard way. or if you went back to first quantization. Except that this becomes a much more handy formalism when you have redefined the vacuum, because you don't need to deal with 100 particles. You just deal with particle hole excitation. And that simplifies the mathematics a lot, and not the least, the bookkeeping.